In this lecture, we are going to discuss about the collision theory for bimolecular reactions. In the previous lecture, we learned what is the collision theory, how the collisions are takes place, what are the assumptions of the collision theory, how the effective collisions are takes place, how we can apply the kinetic theory of the gases, then how we can determine the number of collisions per second per cubic centimeter. Now that collision theory applicable for bimolecular reaction as well as unimolecular reaction. So let us apply the concept of collision theory for bimolecular reactions. Bimolecular reactions means the two reacting molecules are reacts with each other and there is a formation of the product. So in a bimolecular reaction, in order that two molecules must be react, there is a reaction between the two molecules. They should not only collide, but the collision must be associated with sufficient energy. Just the collision is not sufficient to complete the reaction. Okay, the collision must be associated with sufficient energy so that the molecules are activated. During the collision, when suppose let us see, when the collision between the A and B will be takes place, not only the collisions are sufficient, but after the collision the molecules are activated. The molecules should be activated. This means that all the collisions are not effective. All the collisions are not effective. The number of effective collisions is only a fraction of the total number of collisions. The number of effective collisions is the only a fraction of the total number of collisions. Okay. Suppose that total number of the collisions which are expressed there, it is 1000. 1000 number of collisions are expressed. But out of that, the effective collisions, suppose they are only 50. So the rate of the reaction, it is depends upon the effective collisions. The rate of the reaction should depends upon the effective collisions, should not depends upon the number of the collisions. Okay. So talking the specific reaction rate K, rate constant K, as equal to the number of effective collisions per centimeter cube per second. So how we can determine this reaction, specific reaction rate constant K is equal to the number of effective collisions. If Z is the number of effective collisions, if Z is the number of effective collisions, okay, Z is the number of molecules colliding per second per centimeter cube. Remember, what is Z here? Z is the number of molecules colliding per second per centimeter cube in a system containing 1 mole of the reactant, and F is the fraction of those molecules that are activated. So according out of that number of collisions, effective collisions, some molecules will be activated. Okay, some molecules may be activated. So you can see here, once again I would like to repeat this. If Z is the number of molecules colliding per second per centimeter cube in a system containing 1 mole of the reactant per decimeter cube, and F is the fraction of those molecules that are activated, only few molecules get activated. So the rate constant K, it is determined by, it is the product of number of molecules colliding multiplied by fraction of those molecules that are activated. It means that the specific reaction rate constant, it depends upon the number of collisions as well as fraction of those molecules that are activated. Okay. So according to the law of distribution of energy, if N is the total number of molecules per centimeter cube at temperature T, N is the total number of molecules. Suppose that N is the total number of molecules, N. Okay. We have taken N number of molecules for the reaction. Okay. Then N dash is the number of molecules possessing energy of activation. Out of that molecules, N dash is the number of molecules possessing energy of activation, because molecules are goes into the molecules are activated. So N dash is the number of molecules possessing energy of activation at temperature T. Then F can be obtained by the equation. F it is equal to N dash upon N. F it is equal to N dash upon N. What is N here? N is the total number of molecules available for the reaction. Whatever the number of molecules we have taken, so N is the total number of molecules available for the reaction, and N dash is the number of molecules possessing energy of activation. Those molecules who are having the proper energy of activation, that molecules are reacted. Okay, so N dash is the number of molecules possessing energy of activation. Then how we can determine the F? F it is equal to N dash upon N. F is a fraction. Out of that total molecules, how many molecules are activated? Okay, so that is the fraction. So that fraction can be calculated. F it is the fraction here. That can be calculated. F it is equal to N dash upon N. Out of this total number of molecules, suppose that we have taken N it is equal to 6 into 6.023 into 10 raised to 23 number of molecules. Okay, this number of the molecules are taken. Out of that, suppose 2.023 into 10 raised to 23 number of molecules are having the energy of activation, or they will be goes into the activated state. So how we can calculate this fraction? Fraction of the molecules activated. Out of this n dash, so n dash upon n, and this fraction it is equal to e raised to minus ea upon rt. Exponential relationship is there. Okay, so substituting the value of the f in the equation, in the previous equation where k equal to z into f, because k is depends upon z is the number of molecules colliding, and f it is the fraction of the molecules that are activated. So rate constant it is depends upon z and f. So we can determine here f it is equal to n dash upon n, and this value becomes equal to e raised to minus ea upon rt. So if we substitute this into this equation, then we are getting here the rate constant k, specific reaction rate constant k, it is equal to z into e raised to minus ea upon rt. Okay, so this equation is the fundamental equation of collision theory for a bimolecular reaction. This is the equation for the bimolecular reaction. So the theory can be successfully applied to many bimolecular reactions in the gaseous state or even though in the solution state. However, there are many reactions for which the calculated values are found to be much higher than the observed values. Hence, the above equation can be modified like this: K it is equal to P into Z into e raised to minus E upon RT. What is K here? K is the rate constant. What is Z here? The number of molecules colliding. Okay. And P. So what is the P? Where P is the factor P introduced in the above equation is called as a probability factor or steric factor. This is a steric factor. It accounts for the fact that all the collisions between the activated molecules may not result into the reaction. All the collisions in the activated molecules may not result into the collision. So whatever the number of the collisions are takes place, okay, that not result into the reaction. Only those molecules between the activated molecules result into the reaction in which the molecules collide with proper orientation. There should be the proper orientation between the molecules. So the value of the P varies from 1 to 10 raised to minus 9. Okay. So probability factor should be very important here. It means that even though number of collisions are takes place, number of molecules are goes into the activated state, But if that molecules is not having the proper orientation, so if the number of the molecules are having the proper orientations are less, so that value should be varies from 1 to 10 raised to minus 9, p value, probability factor. So when p equal to 1, the reaction obeys collision theory. If this p it is equal to 1, the reaction obeys collision theory. K it is equal to rate constant, it is equal to Z into e raised to minus a upon RT. So this is the equation applicable for bimolecular reaction. This equation is applicable for bimolecular reaction. So in this way, the specific reaction rate constant, it is depends upon the number of molecules colliding, that is Z, and fraction of the molecules goes into the activated state. And that fraction of the molecules goes into the activated state can be calculated according to this n dash upon n. Thus, in this way, we can apply the collision theory for bimolecular reactions.